Hello, this lecture video will tell you about how to use page 8 of the chemistry reference tables in order to answer questions about the absorption and emission of light by hydrogen atoms. The top half of the page shows the Bohr model for the hydrogen atom diagram. It's a little busy, so we're going to start by looking at a cleaned up version of that diagram. On the left, we have the cleaned up version of the diagram. It shows us the hydrogen atom. At the center of the atom, we have the nucleus, which was discovered by Rutherford. And then surrounding the nucleus, we have the electron cloud. And Bohr's main contribution to the model of the atom was the idea that the electron cloud is organized into energy levels, 1, 2, 3, 4, 5, and 6. And the electrons can inhabit only these energy levels and not the spaces in between those energy levels. So in particular, when we're looking at this diagram, we are most interested in these possible electron positions in the various energy levels. And because electrons can only be in the energy levels and not in the space between them, the electrons absorb and emit very particular wavelengths of light, containing just the right amount of energy to move them in between these energy levels. So how we read the diagram, in here we've still got a slightly cleaned up version of the diagram. And so how we would read this section of the diagram is that when the electron for the hydrogen atom moves from the fourth energy level, n equals 4, back down to the first energy level, n equals 1, it emits light with a wavelength of 97 nanometers. All of the numbers on this diagram are being measured in nanometers. However, because going down the energy levels requires the exact same amount of energy that going back up the energy level goes, we can also read this portion of the diagram as saying when the electron moves from the first energy level up to the fourth energy level, it requires the absorption of light with a wavelength of 97 nanometers. So the diagram shows the electron falling back down towards the center of the atom and emitting light, but it can also be read in the reverse direction, saying that it absorbed that light and moved that same trip but up away from the nucleus of this at the center of the atom. The second half of the page is taken up by the electromagnetic spectrum diagram. Remember that light is a portion of the electromagnetic spectrum, but it also includes things that we call radio waves and microwaves and X-rays and gamma rays. These are all made of the same material as light, just of a different wavelength. This half of the page, this diagram, is measured in meters. So we do need to be able to convert between the nanometers on the top half of the page and the meters on the bottom half of the page. And we're going to focus on the visible light portion of the spectrum. This is just a very small portion of the electromagnetic spectrum, but it's one that we care about because we can see this portion of the spectrum. And so the boundaries of the various colors are indicated by the wavelength of light. So looking at red, for example, if I have light with a wavelength in between 7 and 6.5 times 10 to the negative 7th meters, that light is going to be red. So let's say I'm asked what color light with a wavelength of 6.8 times 10 to the 7th meters is. Well, since 6.8 is between 7 and 6.5, that light would be red. But light with a wavelength of 6.0 times 10 to the negative 7th would be orange because 6.0 is in between 6.5 and 5.9. If I had light with a wavelength of 5.0 times 10 to the negative 7th, that would be considered green, because 5.0 is in between 5.7 and 4.9, and so that light would be considered green. You can also read the rest of the electromagnetic spectrum diagram in that same way, except instead of colors, we're now identifying what type of electromagnetic radiation it is. So light with a wavelength of 6.8 times 10 to the negative 1 meters is a microwave. The rest of the electromagnetic spectrum is much broader, and so instead of focusing on the first number in the scientific notation, we then have to focus on the power of 10 in the wavelength. So because 10 to the negative 1 meters is well within the range for microwaves, we would say that light with a wavelength of 6.8 times 10 to the negative 1 meters is considered a microwave. Likewise, light with a wavelength of 6.0 times 10 to the negative fifth, right, would fall under the infrared range, and light with a wavelength of 10 to the negative 11th meters would be considered an X-ray, because that power of 10 falls only under X-ray. There are some places where these categories overlap. And so you're going to have to be very careful when answering multiple choice questions about those places where the categories overlap. The reason there's overlap is because scientists who think that they are studying X-rays say, oh, well, this acts kind of like an X-ray. It's just a slightly different wavelength. So I'm going to call it an X-ray. And a different scientist who's researching UV light goes, oh, that definitely acts kind of like ultraviolet light. It's just a slightly different wavelength. So I'm going to call it ultraviolet light. And then when they come together and talk about their research, they discover they've been talking about the same light. So they just put both their names on it instead of fighting over who gets to claim it. So anyway, this is all the information that you need to answer questions based on page 8 of the reference tables using both the Bohr model of the hydrogen atom and the electromagnetic spectrum diagram. Thank you very much.